Welcome class to the Math 1030 support video for handout for Unit 8A on growth, linear versus exponential. We begin with a comparison. It is a tale of two towns. It was the best of times. It was the worst of times. The mayor of Liontown has been tracking the population for the past 50 years. At that time, the town had a population of 10,000 people. The mayor discovered that the town had been growing at a rate of 500 people per year. Okay? So growing at a rate of 500 people per year is the important part for this statement. Okay? 10,000 people to start. The mayor of Exponent Town has also been tracking the population for the past 50 years. At that time, the beginning, the town had a population of 10,000 people. The mayor noticed the population boom and discovered the town had been growing at a rate of 5% per year. Okay? So this is the key for here, growing at a rate of 5% per year. Each mayor plotted their population growth on the same graph. Which town is which and why? Okay? So the first town is growing at a rate of 500 people per year. So every year they get 500 more people. So I'm just adding on 500 each time. So this town is the line town, the blue line. Now, if you're growing at a rate of 5% per year, you take 5% of the population and add that onto the population. Then you take 5% of that total population and then add on to that. Okay, so each time your population is increasing by an increasing rate there, by an increasing amount. So that means that this one, the orange line, is Exponent Town. Okay. We're going to talk about these types of growth in turn. Linear growth and exponential growth. What is linear growth? Well, linear growth occurs when a quantity grows by the same absolute amount in each unit of time. So linear growth occurs when a quantity grows by the same absolute amount. In each unit of time. Like years or weeks or whatever. And the key here is the same absolute amount. That's the key. It increases by the same amount, like the 500 people per year in our example. What is exponential growth? Well, exponential growth occurs when a quantity grows by the same relative amount or by the same percentage or proportion for each unit of time. Okay, so exponential growth occurs when a quantity grows by the same relative amount. Meaning by the same percentage or proportion. In each unit of time. Okay, and the key here is the same relative amount. Okay, so it grows by % each time. Let's go ahead and take a look at number 2. We want to state whether the growth is linear or exponential and why. Then answer the associated question. A. The number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 4 years ago was 750, what is it today? Okay, so we're going to say, okay, the growth is linear because it's adding the same absolute amount, the same amount each time. Okay, the growth is linear. So in year 1, we're gonna track the population now, the number of students at the school. Year 1, it was 750. I'm going to add 50, and then at the end of year 1, it is 800. At the beginning of year 2, we have 800 students at the school, plus another 50 equals 850. Year 3 is 850. And then you add 50, you get 900. And year 4, we have 900, and we're going to add 50 more to get 950. Okay. So when we ask this question, or when we find this answer here, it took a lot of steps to do it. So how can we shorten the calculation? Okay, notice that I added 54 times right here. So 50, if I keep adding 54 times, then I can actually add 50 times 4, or 4 times 50. Okay. So that's how we can shorten the calculation. We'll take our initial value, add on 4 times 50, which gives us the initial value plus 200, which is equal to 950 students. Okay, so that's our short way of doing it. Let's take a look at the next one. The price of milk has been rising 3% per year. If the price of a gallon of milk was $2 3 years ago, what is it now? Okay. So the growth is rising a percentage per year. So it's not an absolute amount, it's just whatever there is adding on. So percent of whatever there is. This is an exponential growth. Yeah. Okay, so the growth is exponential. Year 1. We start with our $2. We multiply it by 0.03, because that's 3%. And then we get 6%. Therefore, we take our $2 and 6 cents. We add on our 6 cents. And what we get after that is $2.06 at the end of year 1. Let's start with year 2. We're going to calculate year 2. $2.06 to start. Multiply by 3%, which is 0.03, because it's going to be 3% increase. That's going to equal 0.0618. So we're going to take that and add it to $2. And we get $2.12 and 0.218, which is about $2.12. Year 3. we take our 2.1218, multiply by 0.03 to get 3% of it. We get 0.063564. Now we're going to add that onto our $2, 1218 cents. And we get 2.18545459. $2.185454. Okay, which is about equal to $2.19. Okay, so that's 3 years. So how can we shorten our calculation? All right, so what we're doing on each one of these is we're multiplying the total by 0.03. We did that 3 times. So we can actually multiply the totals by 0.03 squared. But what we want to do is we want to be able to add on the $2 here. So we add on the $2 plus our 3%. Okay, so I'm actually adding on one whole $2. Okay, so what we're doing every time is we're adding on 3%. And they're also adding on that 3% to the whole $2. Which is one set of $2. Okay. So shortening our calculation is we take our multiplying by 0.03s and add on the 1 for the one whole $2 and the 0.03. Okay, so what we're going to do is we're going to say, okay, we'll take our $2, multiply it by 1.03, and that 1.03 was cubed because we did it 3 times, 1 for each year. Okay, and that's going to equal $2 times 1.09, which gives the 2.19. Okay, and then we have our answer. Number 3, state whether the decay is linear or exponential and why. Okay, so we have another couple of situations where we're using some decay, which means less and less numbers, less and less amounts. State whether decay is linear or exponential, and then answer the associated question. The price of high-definition TV sets has been falling by about 25% per year. If the price is $2,000 today, what do you expect it to be in 4 years? Okay, so let's see here. Let's go ahead and track the years, and then we'll decide whether it's decay or the decay is exponential or linear. So for year 1, we have $2,000, and it's been falling by 25%. So we multiply that by 25%, and we get $500. That means that, and then we take that $500 and add it to the 2,000, or subtract it from the 2,000, and we'll get $1,500. Year 2, we start with $1,500. Multiply by the 0.25, 25% of it, and we get $375. We minus that from the 1,500, and we get $1,125. Year 3, we start out with $1,125, find 25% of it, and we get $281.25. And we subtract that from the 1125. And we get 843.75. Okay. Year 4. 843.75. Multiply that by 0.25. And then we get 210.9375. Then we take our 843.75, subtract off the 210.9375, and we get 632.8125, which is about equal to 632.81. Okay. So how can we shorten our calculation? Well, we can take our $2,000 so how can we so we take our $2,000 and we multiply it by 0.75 to the 4th power, because they did this twice here, or 4 times, because they multiplied that by 0.25 4 times, and they subtracted off that much money from the whole. Okay, so I'm actually taking 75% of the price every time. So I do that 4 times, and I take that to the 4th power, and that is equal to the 632.8125, which is about equal to 632.81. Is my answer. Okay, let's take a look at another situation here. The tax law that your state has allows you to depreciate the value of your equipment by $200 per year. If you purchased the equipment 3 years ago for $1,000, what is its depreciated value today? Okay, so let's go ahead and calculate the depreciated value, then we can assess whether decay is linear or exponential. In year one, your equipment is $1,000, and you can depreciate it for track the depreciation for $200 a year. So we're going to subtract $200, and I get $800. So after year one, the equipment is worth $800. In year two, we have $800 subtracted $200 again, and that's equal to $600. In year three, the equipment is $600, and it depreciates. We depreciated another $200 to get to $400. Okay. So we want to think about how can we shorten the calculation. So we're going to take our $1,000 and we're subtracting off 3 groups of $200. And use multiplication to help shorten this. That's equal to $1,000 minus $600, which is equal to the $400, okay, which is our answer. Now, which one is linear and which one is exponential? Okay, so the first one is decay. The first one is going to be an exponential decay because I'm subtracting off the same percentage. Okay, subtracting off 25% of whatever's there, 25% of whatever's there. Okay. Is exponential in this one. And the next one, decay, is linear because it keeps subtracting off the same amount. In this example, we're going to take a look at the power of doubling, the effect that it has, and how big things can really get. So there's an old legend that says that when chess was invented in ancient times, a king was so enchanted that he said to the inventor, "Name your reward." "If you please, king, put 1 grain of wheat on the first square of my chessboard," said the inventor. "Then place 2 grains on the second square, 4 grains on the third square, 8 grains on the fourth square, and so on." The king gladly agreed, thinking the man a fool for asking for a few grains of wheat when he could have gold or jewels. Well, to see how the reward works out, let's fill in the following table. We're going to first focus on the grains, the number of grains in each square. So for the first square, we had 1 grain, according to the inventor. The second square, we had 2 grains. The third square, we had 4 grains because we're doubling. So 1 times 2 is 2, and 2 times 2 is 4. 4 times 2 is 8. We have 8 on the fourth square, 16 on the fifth square. We need to determine the number of grains on the 64th square of the chessboard so that we can then get an idea of the entire reward that the inventor gets. Okay. So we need to look for a pattern. Since this is an exponential relationship, exponential growth model, we can express each of these values as 2 to a certain power. Anything to the 0 power is 1, so it's 2 to the 0. 2 is actually 2 to the first. 4 is 2 times 2, which is equal to 2 squared. 8 is 2 times 2 times 2, which is equal to 2 to the third. And 16 is 2 to the fourth, and so on. So to see how many were put on the 64th square, let's take a look at this patterns in the squares, square number, and our exponents. Okay. So the 0 exponent corresponds to the first square. The first exponent corresponds to the second exponent corresponds to the third, 2 cubed corresponds to the fourth square, and 2 to the fourth corresponds to the fifth. Notice that each of my exponents are increasing by 1 as the squares increase by 1. And they are differing by that the exponents are 1 less than the square number. So therefore, the grains on square 64 is going to be 2 to the 63rd power. Oops. Okay. And so let's see how much that is. So in part C, we have, using the pattern in the first column of the table, how many grains of wheat will be placed on square 64? Okay, so let's go ahead and find out what 2 to the 63rd power is. And so when we find 2 to the 63rd power, we get 9 times 10 to the 18th grains. So it's all this many grains. So what we have here are the hundreds, thousands, millions, billions, trillions, quadrillions, and quintillions. So you have 9 quintillion grains of wheat. And that's only on square 64. So what we have here is, part D says, if a grain of wheat weighs 1/7,000th of a pound, how much will the wheat weigh on square 64? So we need to weigh these 9 quintillion grains of wheat. Okay, so we take our 2 to the 63rd and then divide it by 7,000. So what we're going to do is that we have 9, let's do 9.2. Quintillion grains times it by 1/7,000 pounds per grain. And we're going to, these will cancel here. And we'll get 9.2 divided by 7, which is equal to 1,317,624,576,693,539,401. And a little bit more. So it's about equal to this. 1/7 more. Okay, again, we have our hundreds, thousands, millions, billions, trillions, quadrillions, quintillions. So it's about 1 quintillion pounds. Using the pattern discovered in the second and third columns of the table, how many total grains of wheat are on the chessboard? Okay, so let's go ahead and take a look at the total grains thus far section of our board. what we need to see is a pattern. First, we need to calculate how many grains will be on square one. Well, square one has one grain. And square number 2 will have all of what's in square number 1, which is 1, plus the 2 that come from square number 2. Okay, so there's 3 total grains on square number 2. Let me erase these here. Okay, so since square number 2 has 3, we put the we're going to add that to the new amount from square number 2 has 3, so from square number 3. So we have the 3 from square number 2 adding on to the 4 new ones, and we get 7. Okay, so we have on square number 4, we have 7 from all the previous squares, and we're going to add on the new 8, and that gives 15. And square number 5 has 15, plus we're going to add on the new 16, and we get 31. So how many grains will be on square number 64? Okay, so notice, let's see for patterns again. Notice that the total numbers is the same as the one in the future minus 1. 7 is 8 minus 1, and 15 is 16 minus 1. Okay. So what we're going to do is we're going to say, okay, the total for the total grains in here, we have the future square. The next square is 2 to the first, for example. Subtract 1. Square number 2 has the same amount as 2 in the second to the second minus 1 as well. Okay. 2 to the third minus 1. 2 to the fourth minus 1, 2 to the fifth minus 1. Okay. So notice the connection here from yellow, this 2 to the fourth to the previous square minus 1, 2 to the third, okay, 2 to the third minus 1, 2 squared, 2 squared minus 1, 2 to the first, okay, 2 to the first minus 1. Which means that in square 64, there's going to be 2 to the 64 minus 1 total grains on the whole board. Okay. So using the pattern discovered on the second and third columns of the table, how many total grains of wheat are on the chessboard? So what we're going to do is we do 2 to the 64 minus 1. And that is equal to just double, kind of double what we have with the 9 quintillion. So we have 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,000, and 616. That's how many total grains there are. Okay, there's that many grains of wheat on the board. So the total weight is we take this number and we divide it by 7,000. 7,000. Which means so let's just write this in this way. So it's 18.4 quintillion grains times 1 over 7,000 pounds per grain and that's about equal to 2,635, 249, 153, 387, 078, and some change. Okay, so we have hundreds, thousands, millions, billions, trillions, quadrillions. Oh, that's a lot less than what I thought before for up here. I think I need to divide this number by 7,000 and not by 7. Okay, so it's 1,000 less. So we're going to go to, let's erase the last 1,000 here and put a 2 there. Oops, not this one. This one here, the pounds. We'll erase this one right here, the last 3 here. Okay. That's how much it will weigh. In the quadrillions, 1 quadrillion. So we'll re-emphasize that one here. It's equal to 1.3 quadrillion pounds. And this is equal to 2.6 quadrillion pounds. Okay, so now we've got it. That's the end of this video. Hope you enjoyed our explorations. Let me know if you have any questions.